Hi everyone, I'm Taryn Luce. I'm a computer science major at the University of Maryland Baylor, and this is my first year as an Alpha Chi member. I'm really excited to present my research project in New Mexico. Unfortunately, because of recent circumstances, I'm having to pre-record it and put it on YouTube. However, if you have any comments or any questions, please feel free to leave a message in the comments section on the YouTube video and I will try to reply. Let's get started. So, I had a really interesting summer last year. A lot of people traveled or did things like go to the beach or go to Disney World. I actually stayed at my university to work on a research project that I thought was really interesting. The project goal was to develop a real-time particle engine program that could simulate up to and over 100,000 particles at a consistent 30 to 60 frames per second. And I'm sure you're probably thinking, well, isn't there already off-the-shelf simulation software that can do that? There is a lot of software, but this project had a unique application. It's actually part of a larger collaboration between UMHB's Computer Science Department and Nursing Department. A few years ago, the Nursing Department asked the Computer Science Department if we could develop a collection of tools and software that could be used to assist in medical training and simulation. And one of the things that the nursing department was really interested in was a system that could visualize oxygen particles going into the respiratory system and then being exhaled back out as carbon dioxide. And all of these tools are really cool because we're targeting the Microsoft HoloLens as a platform to actually run the programs on. The HoloLens is a unique device because it can project holograms out into the real world. It's a set of glasses that you put on, and it uses augmented reality technology. Now, when we actually started looking at developing for the HoloLens, we ran into a pretty big issue. It uses basically a mobile phone processor, and it doesn't have enough power to handle a particle simulation. So we had to come up with a unique solution. And we thought about different things such as using cloud computing or kind of scaling back our goals to have less particles, lower frame rate. We figured out the best solution would be to build a PC tower, really powerful tower that could get the data from the HoloLens and perform all of the heavy calculations, and then return it wirelessly. And at the heart of this PC, we actually put in a 16 teraflop RTX Titan graphics card, one of the most powerful that NVIDIA manufactures right now. And this card basically does all of the physics calculations. You can see here a picture before we built the computer and then afterwards when it's on and running simulations. Now, the reason we went with the RTX Titan is because it utilizes something called parallel processing. Now, parallel processing is a solution that we first encountered at a mathematics conference at Tarleton State University in Texas. The advantage of using the Titan for parallel processing is that we can allow multiple iterations of an operation to execute at once. So things like calculating position we can do multiple times rather than just for each individual particle. And it works by basically taking a large data set and splitting it into a multidimensional grid of processing threads so that we can have one thread work on one particle at a time. I have a diagram right here just showing sequential processing versus parallel processing and kind of the difference in how they operate. So sequential processing, which happens on a normal CPU, basically works by going from particle 0, calculating it, switching particle 1, calculating that, and continuing on to particle 100,000. And normally CPUs are fast enough to where you wouldn't normally notice that it's only doing one calculation at a time, but as the data set increases in size, as we tell it to add more particles, it starts to slow down. With GPU parallel processing, we can actually work on almost 1,000 particles at once. So it's particle 0 to 1,000 being calculated, then particle 1,000 to 2,000, and so on. And this happens in the same time it would take the CPU to do 1 or 2 particles. Now, the reason we're able to use the RTX Titan as a parallel processor is because the architecture of the modern GPU card is already designed to do parallel processing. When you think about what 3D graphics are to a computer, it's nothing more than a data set of numbers and variables that have to be calculated quickly and efficiently. So that already exists on the GPU. NVIDIA realized this in the mid to late 2000s and developed a library called CUDA that allows us to use the architecture of the GPU for things other than 3D graphics. Now, depending on the GPU model, you can have anywhere from 100 particles at once up to thousands. It really depends on how many threads can be implemented. Unfortunately, parallel processing isn't perfect and it has its limitations. The big limitation is that the graphics card and the actual computer processor are treated as separate devices, each with their own memory. So, if we want to access memory that's in the GPU from the CPU, we can't do that without using a special copy operation that takes a bit of time to execute. So, in order to optimize having to transfer particle data that's been calculated in the GPU back to the CPU, we actually split each particle into 2 sections. The first section contains just a position vector coordinate that basically indicates where the particle is in the environment. And this data is transferred over from the CPU to the GPU, calculated, and then transferred back to the CPU every simulation step. Now the second section is a bit different. It contains vectors for velocity and acceleration that we use in calculating physics. This stays in the GPU because there's no reason for the CPU to access it, and we can save time copying things back and forth by basically just leaving it stationary. Now, the other thing to note is that when we run this in CUDA and on the desktop computer, it's not actually displaying any particles. It's just doing basically number crunching. So we had to develop a second program to actually run on the HoloLens to visualize particles. And we built this program using the Unity 3D engine and the C# programming language. The reason for using Unity over something like DirectX or OpenGL is because the HoloLens development kit is actually already integrated into Unity. So it's easy to port over once we have a HoloLens ready to start up. Now, this is yet another obstacle. We quickly realized that if we're transferring this data wirelessly, we've got 100,000 particles, 3 dimensions. We're trying to transfer 300,000 position coordinates in under a 60th of a second. And first we thought, well, we could put it in like maybe a JSON file or, you know, some kind of XML. Problem is, you add additional data when you transfer it that way. And that causes the file size to expand considerably. So we wanted to get the smallest file size possible. And of course the smallest unit of data that a computer can understand is binary. So we developed an algorithm that takes all of the coordinates of the particle system and then basically turns it into a large binary array of floating point numbers. And then the client has its own special protocol with different codes and functions that it uses to reinterpret this array back into vectors. Now, for the fun part, which is physics and mathematics. It's actually not as complicated of a physics engine as it sounds. The engine uses simple Newtonian mechanics to simulate particles. Our primary algorithm that drives the simulation is Verlet integration. We got this algorithm from a programming manual that was originally in Fortran, so we had to convert it to run in CUDA and run in parallel on our own. But basically what Verlet integration does is we can take a particle's acceleration and then we can integrate it mathematically twice to get its position. And then we send that position over to the HoloLens for display. Now, I want to show you the following video which demonstrates the current state of the particle engine. Currently we've tested different things such as turbulent acceleration, randomized motion, and this will form the basis for the actual respiratory simulation in the future. Thank you for watching, and if you have any questions, please feel free to leave a comment.